Hi everybody, welcome back to Chem 163. It is week 7, which means that we're getting kind of close to the end here. We have a few more chapters to do, so let's just get straight to it. The only announcements that I have for this week are, we're probably doing Lab 3. I haven't heard back from the lab coordinator yet. I'm just checking on the status of the NMR. Usually no news is good news, so until otherwise stated, assume that the lab we're going to do is lab number 3. So you're going to get to play with the NMR and the IR, and you'll also do a polyprotic acid titration, which, Chapter 14, we're still sort of dealing with that stuff because the quiz for Chapter 15 has a bunch of Chapter 14 stuff on it, too. So yeah, we're going to have that going this week. And then quiz number... Or I keep wanting to call it quiz number 15. So the Chapter 15 quiz, I should say, will be due either this week or next week. I haven't decided yet. It's going to depend on how far we get through today's lecture. So I'll make a decision probably by the end of the day, because a lot of these problems that we're going to be doing are just really similar in nature, and so we're going to skip over the later ones because they're almost too difficult to do in a test setting. Not that they're hard to do, but because there's so many parts that they become error prone, and you'll see what I mean as we do this. So, all right. So the first thing that we're going to talk about today is a process called selective precipitation, not participation. And what this basically means is that, hey, if you have a mixture of ions that are soluble, how do you deal with that? How do you separate them out so that you can do chemistry in the manner that you find useful? So, for example, maybe you have these two ions in a sample of seawater. So I have magnesium and I have calcium, but I don't want to have them mixed together. So what you could do is you could use hydroxide. And the way that I know that I could use hydroxide is the following. So I'm going to go to your textbook here. And what we're going to do is we're going to open up Appendix, I believe it's J. And it should just be solubility constants. It should be J because I've been looking at it all week writing your quiz. Yeah, there we go. So let me get this on the screen here. Appendix J. Okay. So this is just part of the screen here. So table of contents over here on the right, we're just going to get rid of that. But this is what Appendix J looks like. It's just a bunch of solubility product constants. And so what you would do is you would say, okay, I have these two ions. What would precipitate both of them? So for example, if I wanted to separate out barium from bismuth's not a good example because I don't really have anything similar. Barium from cadmium, we could do this, it looks like. Yeah, so I would look for a counter ion that both have. So for example, carbonate. So I could, if I added a source of carbonate, say like Na2CO3 as sodium carbonate, then I would precipitate out both of these things because both of these have KSPs. But the one with the smaller KSP would precipitate first. So if I can carefully control the amount that I add, such that when I multiply the amount of cadmium that's in there by the amount of carbonate that's in there, I get a number that is bigger than KSP, a precipitate forms. But also, if I can set it up such that the number I do up here for the amount of barium times the same amount of carbonate added is smaller than KSP, then I won't make a precipitate of this, and then all the precipitate I form must be one of those two things, the thing with the smaller KSP. So this is called selective precipitation. Pick a substance that has the counter ion to the ion you want to precipitate out. You don't want to do cations, you could do anions. So for example, if I had sulfate and carbonate in here, I could add barium. This one would not be super great if I was trying to just add barium to get rid of the carbonate before the sulfate because the KSPs are very similar. But if I had, like, say, phosphate and sulfate, this would be a good choice because its KSP is very small. Now, remember, it's hard to predict Molar solubility relative to KSP if the ions are different. But for our purposes, what we're going to be doing is we're going to be picking ions that have the same number of components that it splits into. So, for example, here we did barium carbonate and cadmium carbonate. They both split into 2 ions, so our KSPs are reliable. Whereas if I did barium phosphate versus barium carbonate, a little less reliable. I'd have to actually set up the molar solubility calculation and like do an ice table to see if at least those S's are in the same ballpark or not. All right, so we're going to be referring to that, and I've provided some of the numbers on the screen here. So you could see that I have magnesium and calcium, and I'm going to precipitate them out using like sodium hydroxide solution. Of those two, which would precipitate out first? Well, obviously it's going to be the one that is less soluble, right? It's the one with a smaller KSP. So magnesium here would precipitate out first. So if I add a low enough concentration of sodium hydroxide that calcium hydroxide doesn't precipitate, but it's enough that magnesium hydroxide will precipitate, I will get only the magnesium out. Oops, there we go. And as long as they have different phases, you can separate them using, like, say, a filter. So you use a funnel and a piece of filter paper, and the solid will stay in the funnel, and the dissolved calcium in the water would flow through the funnel into a collection cup, where you could then precipitate it out and get it later, if you so chose. Now, this is useful, but it's not perfect. And we're going to see what we mean by that in just a second. So we're going to do this example here. So in seawater, here are some concentrations of magnesium. So magnesium is 0.059 molar, and calcium is 0.011 molar. What minimum concentration of potassium hydroxide will precipitate only the magnesium ion? All right, so let's go over here, where everything is blank. There we go. The first time I boot up a scene, normally I toggle between these when I'm doing setup. It has to load, so that's why it just all died there. All right, so I know that the magnesium concentration in my solution is this. And I also know that if I was to do this expression, so what compound will magnesium make when hydroxide reacts with it? Well, it's going to make this. Because hydroxide's a -1 charge, magnesium is +2, so I need 2 of these. And if I were to write out its solubility equation, I would get this. I should put solid over here. And that. So this is the information that I know at the start of the problem. Now, if I was to write KSP for this expression here, that would be equal to the amount of magnesium I have times how much hydroxide I have in here squared. And so you could think of this also as like S and 2S. Well, why don't I put 2 hydroxide in here? Well, this number is already twice as big as magnesium is because it dissociates into 2 ions, right? So this is already accounted for in there. But the squared term isn't, so we do have to include that. Because that's just part of equilibrium, right? That's the law of mass action. Okay. Well, if I know these two, I can calculate for this one, yeah? And whatever number I get must be the minimum number that must be to make this product equal KSP. And if I use a number bigger than that, well, then Q is greater than KSP, and this precipitate will form. So we're going to solve for hydroxide. So let's do that. So KSP divided by the amount of magnesium I have, and then we'll just square root the whole thing, would be the amount of hydroxide I have. So that's going to equal, what was my KSP here? 2.06 times 10 to the minus 13 divided by magnesium, which was 0.059, square root equals hydroxide. And we'll punch it in the calculator, see what we get. So we got that. 0.059, just one O there. And then we'll square root this. It's actually a 7, so let's do that. 1.87 times 10 to the negative 6. So I need to have at least this concentration of hydroxide to precipitate. And specifically, precipitate that, magnesium hydroxide. Now, remember that if I have hydroxide, I could turn this into a pH, right? And if I wanted to calculate that right now, I would just go, so I would log this and go minus. So that's the pOH. And then I would say 14 minus this number. So this solution would have a pH of 8.27. So that's another way that you could just measure this. Instead of asking what's the minimum hydroxide concentration, you could just say, okay, at what pH will this precipitate? So that's just another manner of considering this. But that only works if you are using, like, say, acid or hydroxide. Particularly hydroxide, because a lot of hydroxides are insoluble. And you know the concentration of hydroxide based on the pH because pH is a function of H3O+, and H3O+ times hydroxide equals Kw. Ironically, the place that actually has the most common application would be things like laundry. So laundry is usually done in a basic solution. And the reason for that is because we want to have enough hydroxide in the laundry basin, or, like, say, your washer, such that any metal ions that are in there can precipitate out as hydroxides, which are typically either colorless or, at the very least, they're insoluble, and so they can be washed away. When the water is drained out of the washer, the solids will flow with it and not be on, say, the clothing that you're washing. That can be a particular problem if you have, like, hard water, or if you have water that has various ions in it. For example, manganese will stain stuff purple, which is not something that you really want with your clothing. All right. So there's the calculation that we just did. We calculated that we need this concentration to make our magnesium precipitate. For the next problem, what we're going to do is we are going to add more KOH, and this time we want to figure out when the calcium will precipitate, and also, once we have done that, how much magnesium is left in the solution. So the first step is pretty straightforward. Sorry, I'm just clearing all of this out of here. And that is that we need to figure out how much hydroxide is needed to make calcium precipitate. So we would do the exact same thing first off. So I know that calcium's concentration is... I don't know what the calcium concentration is. Is that written in here? No, we need to go back to the previous problem. Which I'm going to get right here if I can find it. Where is it? There it is. 0.011 was our concentration of calcium. And I know that if I have calcium hydroxide, then its solubility expression would be calcium ion and hydroxide ion. And you can't see this because I need to do that. There you go. And if I were to write out KSP for this, I would get calcium and hydroxide squared. We're going to do this the exact same way because I know KSP, that's known. I know calcium, so let's set up to solve for our hydroxide. And so that'll be, this is a different KSP, so it's going to be 2.06. Oh, that's the other one. So I want 4.68 times 10 to the minus 6. And then our calcium concentration was 0.011 square root. So 4.68 times 10 to the minus 6 divided by 0.011 square root. 1 sig fig is what we get here. So you can see that's way more concentrated. That's like pH 12. Oh, what did I do? What's really cool? Or maybe you're a few minutes behind. I'm not sure. All right. Anyway, so if I add this much, then calcium hydroxide will precipitate. Oh, the laundry thing. Oh, yeah. Yeah, that's actually why we do, like, so bleach is basic. And, like, the bleaching agent is useful to get rid of, like, say, dyes, because dyes will oxidize. Sorry, not dyes, but stains. Stains will be oxidized by sodium hypochlorite, which is the active ingredient in bleach. But also, because sodium hypochlorite, let me just write that in blue real quick. This is just our aside. This is sodium hypochlorite, which is our bleach. This is a source of this ion, which, as we know, is a weak base. So it makes the solution basic. And then the hydroxide that's in the solution does all the aforementioned things with laundry. So there's chemistry in everything. That's why I find it so fascinating. And you should too, because your grade depends on it. No, you can do whatever you want. I don't care. All right. So back to this problem that we're working on. Calcium hydroxide will precipitate at this amount. So if we go back to the previous example, and I make like a little scale, this amount was the minimum, and this is just for a curiosity. Precipitate. We'll just do something like this. So as long as you picked a concentration in this region, so between these two numbers, so 2 times 10 to the minus 6 and 2 times 10 to the minus 2, you would only precipitate out magnesium. So on this side of the line, if you have a concentration less than 1.9 times 10 to the minus 6, so over here, nothing precipitates. Over here, magnesium 2 plus precipitates. And over here, both precipitate. Now, if you ask the question, hey, can I precipitate just calcium? Then the answer to that is, using hydroxide, no. Or, well, sure, you could, but precipitate out the magnesium and then funnel it away and separate it using a filter or something. And then you could precipitate the calcium by adding more base. Now, this doesn't answer the question that's being asked on the screen, as you can see. How much magnesium is left when the calcium begins to precipitate? Well, we do know that this is the amount of hydroxide that is necessary to make our calcium precipitate. So what we're going to do is we're going to go down here, and we're going to say this, because we had this expression for KSP on the previous problem, right? And I know what hydroxide is. It's just this number right here, so I'm just going to plug it in. And I know what KSP is, so we can figure out what magnesium is. Remember that Le Chatelier is going to say, well, if I have this as my expression, I forgot 2 here. There we go. And I make this number really big, I'm going to drive the reaction in this direction towards the precipitate, right? In other words, the more hydroxide I add, the more precipitate I get. And this number is going to be reduced as a result so that I could also consume the hydroxide that I've added. So I should be expecting a really tiny amount of magnesium. And you totally do get that. So if I say KSP divided by hydroxide squared, that'll tell me how much magnesium is in here at this concentration of hydroxide. So that would be so that's KSP for magnesium hydroxide. And then our OH concentration was, I don't remember, 0.021. And you could probably already tell that by looking at that number, we're going to have such a tiny amount of magnesium left. So divided by, I want to do parentheses, 0.021 squared. All right. So that would be the amount of magnesium that is left in the solution when I have put enough hydroxide in there to start to precipitate out the calcium hydroxide. So by the time that I precipitate out calcium hydroxide, how much of the magnesium have I got? Well, originally the amount that I had was, what did we say it was? Oh, I can't find the number. Oh, it's because my slides aren't working here. I'm looking in like the previewer and just trying to find numbers here. We're not in the common ion effect. Where are we? .059. There it is. That's the number I want. So before I did the precipitation, I had .059. Now I have 4.7 times 10 to the minus 10. So if I do our number divided by 0.059 and then times that by 100%, this is the percentage of magnesium that I have left. 7.9 times 10 to the minus 7%. In other words, I have precipitated out this much. So 2, 3, 4, 5, 6, 7. Which is pretty damn good, right? If you, like, cleaned up 99.99993% of your house today, I would not criticize you. I would say that's pretty damn good. Oh, very good. I'd also question how you knew that you had left 7 times 10 to the minus 7%. Actually, this is a percent, so I get 2 more 9s in here. Like, that's insane. Sorry, as a decimal, it would have been times 10 to the minus 9, so yeah. So we can separate these out really well, and the entire reason that we can do that is because these KSPs are so different in magnitude. So the farther those are apart, the better you can do. Now, this is super important in things like water quality. If you have hard water, because you live on a farm or something. So I grew up in the countryside in California, in Central California, and we had to use well water, because the river. I live next to the San Joaquin River, and it's fairly far away. But because there's a river nearby, there's a water table in the ground that's accessible, and so you drill wells. That's what everybody does in the countryside. You drill into the water table and you get water. The problem with that being is that when you do that, you don't really know the quality of the aquifer you're drilling into. So like it could have like iron deposits or magnesium deposits or whatever, and so you might get lots and lots of something. Case in point, when my family bought a house, and we put it on the property, we drilled a well which was like, I don't know, like 400 feet away from where the previous well was, where we used to live. So I literally moved 400 feet down the street, because it was on the property that we had, and we just put the house there. The first time that I used the shower, the water came out, it was orange. Because we had drilled into an iron deposit. And so you need to precipitate out the iron so it does not get into the water supply that you are using, and then traumatize the small child who is in third grade using the shower. Like, why is it orange? Why is the water orange? It had iron in it, so it doesn't freak me out now. But we installed a water softener, which does ion replacement, which is similar to this, basically. And no problems. So just some examples of things that you can do with water quality here. So, all right, we're going to precipitate out lead and silver using sodium chloride, because these both form insoluble chlorides. Silver chloride and lead chloride are both selectively soluble. Now, you can see here that lead chloride is both a larger KSP, and it also splits into two ions. So this is actually going to be a good choice here. But do note that these split into different ions because lead and silver have different charges. So what I want you to do is tell me how much sodium chloride will precipitate out the first thing, and which ion that will be. And then tell me that when the second ion begins to precipitate, what is the concentration of both the chloride so when I say each ion, what I mean here is the chloride and whatever ion has already started to precipitate, because the concentration of the other ion will just be the listed number here, right? All right, go ahead and try these, and we'll go over the results in like 5 or 6 minutes. Yeah, we'll do that. 1 or 2 more minutes, and we'll go over the answers. All right, let's solve the problem here. Scrolling. I should really just do this. Not that you could see what I'm doing here. I'm sitting here scrolling the scroll bar up, which you could see on the side here, and I'm like, oh, I can just click on it, right? You could set it wherever you want to. All right, let's get this on the screen here. Then I'm going to make this smaller so that I can show what numbers we have on here. All right, so which of these is going to precipitate out first? Well, it's going to be the one with the smaller KSP, right? So that's silver. So AgCl can dissociate into silver and chloride ions. And we can figure out the minimum amount of chloride that is needed to do this. So that would be KSP equals Ag and Cl minus. And so the amount of chloride that would be needed to do that would just simply be that much, which would be 1.77 times 10 to the minus 10. It's just a little too tiny for me to read this. I can make this bigger, though. Yeah, there we go. And then what is the amount of silver that we have in here? 0.020. I don't even need square root, so this is everything that we have, so. Divided by 0.02. And I want scientific. There we go. So 8.9 times 10 to the minus 9 moles per liter. So if I had this concentration of chloride, I could precipitate out silver. Now, if I did the same expression, like, let's suppose that you had KSPs that were similar, and they had different numbers of ions, and you just weren't sure. Well, then you just do the other KSP, right? And you could check that too. Right, because the squared might screw things up. Who knows? And so we could solve for the amount of chloride for the lead concentration. Then we just pick the one that's the smaller number, right? So if it's ever ambiguous, you could just do the other one. And then you could directly compare the numbers and say, oh, okay, this one's smaller. And I can almost guarantee that this is going to be a larger number because KSP is just so much bigger. 1.17 times 10 to the minus 5 divided by whatever lead is, 0.08. And then square root. Yeah, you can see that this is just 0.012. So very clearly, the silver ion is going to precipitate at first. And then, what is the concentration? Oops, sorry. What is the concentration of each ion in the solution when the second ion begins to precipitate? Well, here's what the chloride concentration is once we precipitate the second ion. What would the lead concentration be? Well, it would just be whatever the lead was because it's starting to precipitate, right? So that would be wherever I've written that. That'd be 0.0880. And then what would silver be at this concentration? Well, we just take this expression right here. Oh, you know what? Why am I circling it with a pen when I could circle it with this thing and go paste? We'll just put it down there. And then I realized as soon as I did that, that this is not the expression that we're solving for, so I got to do this. And just switch these two. Because we already know chloride. We don't need to know that. So, if I just take this number and put it right here, what was KSP for silver? 1.77 times 10 to the minus 10? Was it? Yeah. And so this will be like 10 to the minus 8 or something. Wait, what? Oh, I typed in the wrong number. I'm sorry. I said the number that I was expecting, and then I typed in that number. Divided by 0.012. Yeah, there we go. That's more like it. So I got 1.48 times 10 to the minus 8. Which should be 1.5 because sig figs. Nobody likes sig figs. I get it. I get it. There we go. So there's the concentrations of all the ions. Now, you could do subtraction to see how much this is actually affecting your result. But remember, for silver, there's so little of it left that it's not really going to take much of the chloride. And the chloride needs to be at least that amount before it will precipitate. So if you use any of it up, you're going to have to replace it before further precipitation occurs. So it'll be about that number. So you don't really have to do any subtraction. All right. So with that all in mind, there's a lot that we can actually do to manipulate solubility. So we can selectively precipitate stuff. What we can also do is we can discourage precipitation or encourage precipitation. For instance, if I have like a solution of, say, I don't know, let's do lead chloride. And so it could do this, for instance. This is really toxic. And we don't want this. So what we could do is, using Le Chatelier's principle, what if I increased this number? So if I just filled the solution with sodium chloride, so I made it salt water. If this number is really big, then when I calculate the reaction quotient here, which would be this number, and this number was way too large, then as a result, Q would be greater than KSP, right? And because of that, the reaction would shift left. In other words, in order for me to use up the excess chloride that I added in there, I would remove some of it along with the lead to form more of this, which is a solid, and I should have written that. So this process is called salting out. You can salt out ions by adding additional ion that is common to the substance that you are trying to prevent precipitation for. And this is also known as the common ion effect. And the common ion effect is purely just a consequence of Le Chatelier's principle. Something is soluble in a solution, but it is less soluble if that ion is already present. Because the presence of products would drive the reaction back towards reactants, right? That's Le Chatelier. So let's look at some examples of this, and then we'll take our break here. So if I have calcium fluoride's not very soluble in water, but if I have sodium fluoride already in the solution, calcium fluoride is even less soluble. And so you can see here, if I add another substance, such as sodium fluoride, that would mean that the amount of fluoride in the solution is a larger number. We could see that in action by just doing a problem here. So let's see what the solubility of calcium fluoride is in regular water. And then we'll do a solution that has 0.1 molar fluoride in it. And then the common application for this is naturally, well, what do we use fluoride for? Hey, toothpaste. So this problem is basically your teeth. So imagine that we are trying to prevent your teeth from dissolving, because that's probably a good application, right? You don't want your teeth to dissolve. Your teeth are not calcium fluoride, though. They're a different calcium hydroxide substance that we'll talk about in a second here. All right, so for this first problem, we're going to set up this ice table. And what I'm going to do is I'm going to immediately copy and paste this. Copy, 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 paste. And we're going to shove this down here somewhere. Oops, that didn't quite work. Okay, because we're going to come back to this in a second. So for the first problem, what we're going to do is we're going to just do this in water. What is the solubility? So this is a solid. We don't care. There's none of this to start. When we dissolve this, some amount will dissociate. And because there's a 2 here, some amount times 2 will dissociate. So we get that. And then we would say KSP for this substance would be S times 2S squared, or 4S cubed. And therefore, KSP over 4, and then the whole thing cubed rooted, would be the molar solubility. In other words, how much dissolves. And so that's going to be 1.46 times 10 to the minus 10 is KSP. Divide by 4, and then the whole thing is cubed rooted. So let's see how soluble this is in just regular old water with nothing else in it. So that number divided by 4, raised to the power of 1 over 3. That looks really weird to me. Hold on. 10 to the 11. I don't know if that did what I thought it should do. Because I should get like a number that's 10 to the minus 5, I would think. 10. So 10 to the minus 10 divided by 4 is that. Okay, that checks out. And then this number raised to the power of 1 over 3. Yeah, that's more what I expected. Okay. I get another number. Okay, 3.32 times 10 to the minus 4. Okay. That was weird. I don't know what button I hit, but I must have hit the wrong key. All right, that's how soluble calcium fluoride is in water, i.e. not super soluble, right? All right, we're going to do the same problem again, and we're going to compare the result. But this time, I'm going to add this, which dissociates into these things, and you can see that one of those is already present. So how much calcium do I start with? Well, there's none. But how much fluoride do I start with? Well, I have this much. And then I do the same problem. But then I get this number over here. And when I solve for my KSP expression, which is going to be the same thing, we're the same setup. I have that 0.1 in there already. Now, this looks like a quadratic, so we could go to Wolfram Alpha, but almost certainly S is small, right? Almost certainly, compared to 0.1. So that's going to make this just become this expression. And that's trivial to solve for. And so that would be, KSP is 1.46 times 10 to the minus 10 divided by 0.1 squared. And that should be 10 to the minus 8. Yeah, there you go. And so you could see that compared to before, where our solubility was 3 times 10 to the minus 4, by adding 0.1 molar fluoride, the solubility went way down. Now it's 1 times 10 to the minus 8. So we have salted out the calcium fluoride and prevented it from precipitating, because one of the ions that it would precipitate into, or I'm sorry, we've prevented it from dissolving, because one of the ions it would dissolve into is already present. And that forces the equilibrium back towards reactants, as you can see there. All right, I overshot the break, so we're going to go take a break. So let's put this on the screen. I don't have a timer. I never have a timer. You guys are my first class on Monday, so it's like, where's the timer? Oh, I forgot to put it on screen. Okay, so I'm going to hit this button, and then I'm going to hit this button, and peace out and relax for 10 minutes. There we go. Let me turn this down real quick. Alright, so on the screen, I have a problem that's more or less the same problem that we just did, but hey, you get to try it now. So I want you to tell me how soluble calcium fluoride is in a solution that contains 0.3 molar calcium nitrate. Now, you'll notice that I'm salting out the other ion this time. I'm going to salt out calcium. So what will be the effect on it? I don't know. I haven't done the calculation. So go ahead and try that and tell me what the reduced solubility is. We've actually already done the second question here. What is the molar solubility of calcium fluoride in pure water? Well, that's just this number. Because we did calcium fluoride, right? Yeah, so we've already done this problem. I can't write on that screen. I need to go over here. 3 point. Right, so I want you to compare the result that you get for the first problem here when you've salted out calcium. And let me know, like, what percentage solubility is, or how many times more soluble, or whatever. You should get a giant number. It should be like 100 to 1,000 times more soluble. All right, go ahead and do this. I'll give you 5 minutes. So see you in a bit. One more minute, we'll go over the answers. All right. Let's go over here. And I don't know if I have my table pasted again, so... Oh, you know what I can do, though? Hold on. Yeah, look at that. That was nice. I could just turn off layer 2. And we'll just go back here. All right, so we've got 0.3 molar calcium. So that means that if this is what we've added in here, then it's going to dissociate into calcium and nitrate. Now, this one we don't really care about because it doesn't match any of the ions that we have. But if this was 0.3 molar, then this will be 0.3 molar. And so I get this as my result. And so KSP will equal 0.300 plus S times 2S quantity squared. And that's quadratic, and we hate quadratics. They are awful. So we're just going to say S is small. And you could check these if you wanted to. You check S versus 0.3 and see if it was actually small. But honestly, we really don't need to do that. Because now this will become KSP equals 0.3 times 2S quantity squared. So this will be 0.3 times 4S squared. And 0.3 times 4 is 1.20. And so now I'll just divide by 1.2 and square root it. I don't know why I almost did this. Like, I'm just habit, I guess. All right, so KSP was 1.46 times 10 to the minus 10 divided by 1.2 and then square root it. All right. And then compared with water, what was our amount for water? 3.32 times 10 to the minus 4. So you could see that it had an effect. It is slightly less soluble now. Now, because it's not the one that we square for KSP, it's not going to have the biggest effect, but it definitely has some effect. I'm just double checking my math. Did I do my math right? 2 squared is 4. 0.3 times 4 is 1.2. Let's see here. I just want to make sure I did this right. Sometimes I just don't trust Windows Calculator. That's my issue. 0.3 times 4. That looks pretty good. Okay. 1.1 times 10 to the minus 5. Yeah, okay. Alright, looks good to me. Alright, so we can approach this now from the perspective of pH as well, because remember that pH affects how much H3O plus is in solution, and also how much hydroxide's in the solution. So we can play with those to either salt in or salt out ions. But there's also another application that can come up, and that is, what if our acidic or basic solution reacts with one of our ions and then consumes it? That would actually increase the solubility. So let's look at an example of this. So magnesium hydroxide, this is actually milk of magnesia. So if you have an upset tummy, you might actually take this. So this is milk of magnesia. And if you've ever taken milk of magnesia, you know that it's this like white suspension in like a syrupy liquid. The white powder that is suspended in there isn't actually dissolved. It's just a solid. It's a precipitate. And it's magnesium hydroxide. Now, if it's insoluble, you might think, well, why am I consuming it if it's not going to dissolve? Well, it does react with acids. And the reason for that is because if this were to dissolve, you get this equilibrium, which means I would have these things in solution. And if I had acids, such as like HCl in, like, say, your stomach, HCl would see this and go, oh, I'm going to react with that and remove it from the solution. Well, if I'm removing a product from the solution, what happens to the equilibrium? Well, it moves in this direction, right? And then more dissolved. So we can tinker with an equilibrium by not just salting out stuff by adding in an ion that already exists from our dissociation of our insoluble compound, but we can also react with the stuff that dissolves. And if we remove that from the solution, then we're going to encourage further reaction. Now, if I had a low pH and I had lots of hydroxide, this would go in the other direction. So the solubility for this is very, very heavily influenced by pH. So at low pH, this gets reacted and the reaction goes forward. But at high pH, which means there's lots of hydroxide, this gets salted out and the reaction goes backwards. So pH can control the direction of solubility and increase either the solubility or decrease it. So that's kind of cool that we can do that. What's not cool is that I flipped what I wrote with what's on the slide, so now everything is upside down, but that's okay. All right. Let's talk about some consequences for that. Particularly, this is Carlsbad Caverns. On the screen is a picture of a system of caves that I believe is under... Oh, I'm going to show my lack of American geography here. I got to look this up. Carlsbad Caverns. I want to say New Mexico, but it might be Arizona. Oh, thank goodness, it's New Mexico. I was right. So I've never been, but I had a Carlsbad Caverns t-shirt as a kid, and I'm like, what did the t-shirt say? I can't remember. Anyway, Carlsbad Caverns are basically a ton of natural forming stalactites and stalagmites. And you can see that here on the screen. What stalactites and stalagmites are they tend to be things like calcium carbonate. They're basic ions that that form precipitates that are insoluble in solution. Now they're insoluble, hence you can see that they're solid right here. And the reason that they're solid is because water drips down from the surface here. So the surface is above. We have water that has these ions dissolved in it. For example, maybe not hydroxide necessarily, but carbonate for sure. And as it drips down here, it plates out as insoluble, and you get solids that then extend down to the floor. And then any place that like water drips down onto, you form stalagmites on the ground. I don't remember which one's the stalagmite, which one's the stalactite, but they eventually meet and you make a column and it's cool. But the reason that this happens is because these ions become soluble up here on the surface, because the pH up here of water tends to be much higher. The pH of rainwater is about 5.5. This is due to CO2 in the atmosphere forming carbonic acid, which is a weak acid, which creates pH 5.5 rainwater, as opposed to what you'd probably expect rainwater to be, which is pH 7, but carbonic acid lowers it a bit. There are other pollutants in the air, too, that lower the pH of water. So, for example, if you get any sulfuric acid in water, then the pH goes down a lot. I'm trying to remember if we talked about... I'm sure I showed you like the America map, and we said, where's all the steel pollution come from? Oh, it's Pittsburgh. The pH of the rainwater over there is much lower than, say, over here. Suffice it to say that the conditions for water and such are much more acidic on the surface, and so things are more soluble on the surface. But all of the water ends up going into the groundwater supply anyway, which means that it eventually filters and funnels down into the Carlsbad Caverns. I mean, presuming we're talking about locally here in New Mexico. As it does that, the acid gets neutralized by other bases that are there. So any carbonate that's around, any hydroxide. These neutralize the acids. And when there's excess of those things, the calcium and magnesium then start to precipitate out. And so you get natural rock formations like this. And it's really cool. So caves are a result of chemistry, believe it or not. They're also a result of just like poor water control. But if you've never seen the Carlsbad Caverns, and this is like a memo for future me, go see them. Like, they're really cool. I've seen tons and tons of pictures of them, and I had family that went, and they brought back pictures, and it's just, like, it's such a cool experience. Alright. So, what we're going to do here is we're going to try and predict what will happen to the solubility of these substances if I subject them to acids. Now, we're not going to subject them to bases because I don't have any acidic counteranions, so... But what we can do is we can say, okay, well, what are the ions that these all split into? So I can do that. And then we'll do the same thing over here. And then I'm going to do this instead, just to give myself some more space here. And so what I want to do is I want to say, okay, if I'm going to add an acid here, which of these will be affected? Well, acid's not going to affect these ions, right? We don't really care about these. So I'm going to just ignore those. But let's look at the anions here. If I add H+, will that interact with F-? Well, F- is a weak acid. Or I'm sorry, F- is a weak base, which means it would react to form its conjugate, right? So, in other words, this would react with strong acid. What about HI, though? What about iodide? This is neutral, because HI is a strong acid. So, would it react with acid? I- would not. Because HI is a strong acid, it would not recombine to form HI. Down here, hydroxide is a strong base. It would definitely react with H+. So what we would do is we would say, okay, if I add acid, the solubility of this one and this one should increase. And this one right here should stay the same. So we've predicted that based on the reactivity of these substances with acids, due to the fact that the anions that have formed are various forms of weak bases, strong bases, or not bases. All right. I'm going to give you some of these now to try, and I want you to tell me, oops, apparently nothing. There we go. Of these two things, which one is more soluble in acid? This should take you 1 minute, so I'm going to just go quiet for a minute. I'm going to go get more water because I just drank all my seltzer, and when I come back, we'll talk about it. All right, which of these will react with acid and increase its solubility? Well, let's look at the ions that dissociate into. All right, which of these ions will react with an acid? Well, we don't care about the cations because they're already positive. They're not going to react with acid. But of these two, carbonate sure will, because it's a weak base. And this is neutral. How do you know? Well, the conjugates of these, HCO3 is a weak acid, HBr is a strong acid. So therefore, H plus would only react with the weak base. It would not react with with Br. So adding acid, I would expect the solubility of iron to carbonate to increase, and the solubility of lead to bromide to remain the same. All right. Guess what? That's it for chapter 15 in terms of stuff for your quiz. I have covered everything that I put on the quiz that I thought was relevant, because the next sections are going to contain. So we're going to talk about Lewis acids. So I'm going to give you some multiple choice questions on Lewis acids on the exam number 2 in the final. No huge deal here. I just want to talk about what Lewis acids are. We're going to talk about formation constants Kf, which is just it's another equilibrium problem. Yay! And then we're just never going to talk about it again. And then the last section is multiple equilibria, which is basically just, okay, how many different ways can I put this together into a math problem? And what I've learned about that last section is that if I test you on it, making any minor error becomes impossible to diagnose, because I have a problem in the equilibria problem that deals with photography, and it takes 4 slides for me to go through the answer. So, when I do that problem in class, and the problem is, and I'll talk about it a little bit, but we're not going to actually do it. The problem to be solved is I have photographic paper, which has silver bromide on it, and that is insoluble. How much sodium thiosulfate do I have to add to it in grams to completely dissolve it? And it's a 4 whiteboard problem. So, that's the sign when you know you're going to do serious calculations, is when the instructor pulls up the projector screen so that it's no longer covering half the whiteboard. And that's that type of problem. I don't want to throw that on a test. If you do that, it'd be 4 pages of your calculations, and you lose a minus sign somewhere, and then everything is wrong, right? I don't want to grade that, so I just don't ask you questions from the multiple equilibria question. portion. So we'll just talk about that when we get there. Let's talk about what Lewis acids and bases are, though. Lewis acids and bases are important because they don't fit the Bronsted-Lowry definition, and yet they still impact pH. And the way that this works is by following a different mechanism. And so the mechanism is Lewis acids are electron acceptors. For example, I'm going to just do this as my example. This is aluminum. If I were to draw the Lewis structure of water, this is where Lewis comes in, because we're going to care about Lewis structures. Oh man, I haven't done Lewis structures since 161, Professor Wes. Well, I hope you know how to do them, because we're going to use them a little bit here. And then remember, the final's cumulative, so. What's going to happen here is that I'm going to form a covalent bond by doing this. And the result that we get is something that looks like this. And then water is going to go like, oh, wait a second, I don't want to be positively charged. Don't be ridiculous here. And so some of the electrons are just going to come back on water. And then this guy's going to be like, huh? And the end result is that you get something that looks like this. I really didn't want to put the H down there, but that's okay. And. We'll put an and there. So you can see that by doing this, water has gotten rid of H plus to reduce its charge. So we have formed an acid. We have donated H plus to the solution by virtue of just being aluminum. And so in the acid-base chapter, we said anything with a positive 3 or higher charge will do this. And this is the mechanism by which it does it. So this on the left here, my aluminum, is my Lewis acid. And I can't get the selector to work. There we go. Now, what do you think that makes a Lewis base? Hopefully you said electron donor. So a Lewis base is just the opposite. It's the substance that donates electrons. And the most common use of this is going to be with metal cations. This explains the acidity of metal cations effectively. However, the Lewis definition actually does apply to all of the acids and bases that we have done so far. So it is actually technically the most complete. So for instance here, if I have H plus and then hydroxide, like duh, base, right? Duh, acid. But who's donating the electrons? Well, these electrons are going to be used to make this bond between H plus and OH minus. H plus has no electrons, so it can only accept them, right? So there you go. There's your electron acceptor versus your electron donor. Now, because this perspective is very bizarre to think about over and over and over again, we give you the Bronsted-Lowry definition first. And we consider acids and bases from the perspective of where's the H plus. But in reality, and I've said this many times, and I'll say it many times again, no matter how much I teach Chem 161, 162, 163, chemistry is all about electrons. The only thing we give a shit about are electrons. And so it makes sense to define everything from the perspective of electrons, because that's where the chemistry is happening. All right. There's the example I literally just showed you. Oh, it's 3 minus. I was looking at that and I was like, is that a typo? But no, it's not. Okay. All right. Now, these things that are attached here, so when I attach stuff to my metal cation, oftentimes we end up with a charge. And the reason for that is because we're not forming necessarily a compound like this, which would be a solid. Like, if I was to like dehydrate this, then sure, I might get 3 hydroxides per aluminum and form that into like a crystal lattice. So, but if I have this as an aqueous solution, so this is all aqueous here. What ends up happening is that my groups that I am attaching to my metal cation tend to occupy all the possible positions that they can, with or without regard to charge. And so this is something that happens very commonly. And because we're forming covalent bonds and doing this, we get an interesting field of science called organometallic chemistry. This is my master's degree. Literally, I am an expert in organometallic chemistry, or at least what I can say is I was when I got the degree, and I haven't really touched it since then. I know enough to get by, though. Organometallic chemistry is literally just adding and attaching these things called ligands, and I think that I introduced what that's called in a second here. Or did I do that on the previous slide? I don't know. So these are called ligands, and ligands basically operate in the same manner as Lewis acids and Lewis bases. So I attach things to my metal center, and I form these covalent bonds. But these covalent bonds are kind of weak, and so these things can just pop on and off however they want to. So you can exchange ligands. Water is a really good ligand. It pops on and off. You've seen water as a ligand already in, say, Chem 161 when we did the molar formula of a hydrate, where you had the copper sulfate and you dump it in the water and it turns blue. And then when you heat it, it turns brown or tan or whatever. The blue copper in water is because it has 6 water molecules hydrating the copper 2 anion. So we've actually seen a lot of this all along, but it's never really been explained until now. Now, this type of bond is actually kind of special. When we formed covalent bonds in 161, what we would do is we do something like this, right? So carbon has 4 valence electrons, hydrogen has 1, and we'd each share a valence electron to make a covalent bond, right? Why am I being messaged? Oh, I bet it's from students. Yeah. We're just going to mute that right now because I'm in class. I forgot to mute during my lecture. So this is a covalent bond. I've shared 1 electron, and so that would have been this electron from carbon and this one over here. In a coordinate covalent bond, both the electrons come from the same thing. And are used in that manner. The end result is the same. You make a covalent bond. It's just that both of the electrons come from one source. So in this case, hydroxide, or the oxygen on hydroxide, is not getting a great deal in terms of sharing electrons because it's providing both. But the overall result of this is that the overall charge is reduced. This is a +3 charge. This is a -1 charge overall. And so the total charge by adding one of these goes from +3 to +2. And if I keep doing that, I eventually get a much lower charge. Oh, there's where I talk about ligands. Okay, so water can be a ligand. That's great. The thing about ligands is that you can exchange them for other ligands. Ligands have different strengths of covalent bonds. Things like chloride and water are terrible ligands, so they pop right off. Ammonia is a much stronger ligand because it acts like a base, so being a Lewis base is not all that different. We did this in the first lab where you added copper to ammonia. When you added copper to ammonia, it turned dark blue or purple. And the reason for that is because ammonia was becoming a ligand and attaching to the copper and exchanging with water. The copper solution was initially light blue, And then when you exchanged water for ammonia, it became very, very dark blue. Oh, yeah, here's an example of that happening with ammonia on silver. So this is a reaction that can occur. I can swap out my water ligand for an ammonia. And what I could also do is I could figure out what the equilibrium constant is for this. And we're going to do that. We're going to assign it this. So this is called Kf, or the formation equilibrium constant. Now, depending on the ligand that you use, Kf's become these ginormous numbers. Kf is essentially the opposite of Ksp, but we use Kf for these complex ions. So specifically, Kf is for the formation of complex ions. So there's an example Kf right there. You'll notice that in this equation, all I've really done was omit water. So if I do this and get rid of this, and then I don't care about it over here, I get the same expression. Kf's are usually really big. And the reason for that is because we write them in a manner that produces a complex ion. And complex ions do tend to form pretty regularly. The reason being is that if I have a metal and it has a positive charge, something with electrons on it is going to be attracted to that. So the formation of an ionic complex, even if the overall charge isn't reduced, negative things are attracted to positive things, right? So they're going to just collect together, and then whatever result ends up happening is what happens. So formation constants from the addition of ligands to metal centers are very, very large. If you are doing homework practice, like, just for the hell of it and trying to do more complex equilibrium problems, we have a bunch of formation constants. I believe that's Appendix K. And let's just get that on the screen here so that you can see what these constants look like. So, boop, there we go. And so you can see that these are all ginormous numbers for various ligands that can be added. Now, there are all sorts of different ligands here. I've already found a typo. There should be a minus on the cyanide, like all the other ones have one. But these are all ginormous numbers. And that's it. That's all of them. There are tons of them out there, but your textbook only has these here. And virtually all of them will have some sort of charge left over. And they're all soluble in water because they're all charged. So that's really all I have to say about these. So, oops, I misclicked something and then OBS disappeared. Hold on. No. There we go. All right. We're not going to do any problems using formation constants because at this point, I'm just like, I'm equilibriumed out. I want to get to the fun stuff. I want to talk about freaking batteries, that's what chapter 17 is, or 16 is batteries. And that's what we're going to do on Wednesday here. So let's just finish this off. So if I wanted to figure out how much copper was in here, what I would do is first, I'm going to show you how I would solve this problem. So I'm going to mix this with ammonia. So here's what I would say, okay, the copper ion is going to come from this. Nitrate is the conjugate of it's the conjugate of a strong acid. So nitrate does nothing. I don't give a shit about it. This must be the complex that I form. So I would write an equation like this. And then I know what Kf for this is. So I could write Kf equals how much of this I made Oops, I gotta put the 2 plus in there. Divided by copper 2 plus. And then ammonia to the 4. And then really, this is just a matter of, okay, well, if I write out an ice table, and then I do X is small, and I can get all the concentrations right, I could solve it, right? You've done so goddamn many of these, right? We don't want to do any more. We're so sick of it. So, I trust that you know how to do this, even though this is a more complicated problem. I'm not going to test you on it. We've done enough of them, right? So you can set up ice tables, figure out what these amounts are. And you'll find out that the amount of copper that you get out of this, really, really small. And the reason that it's really small is because KF is fucking huge, right? It's so big. If KF is that big, we have to use up almost everything, right? And thus, there can't be that much left. All right. So, again, don't care. Not going to do these problems. This is more or less just talking about... Oh, okay, yeah, let's talk about this a little bit. We'll do this for the last few minutes. And then we'll actually finish chapter 15 on Wednesday, as I just talk through the rest of it. If you want to improve the solubility of something and you have this table... Because, oops, I'm scrolling on the wrong thing here. Because all of these have extremely large formation constants, if you have a compound that has, like, say, I don't know, nickel in it, or iron or something, and you really want to dissolve that, then you could do something like the following. So let's go over here. And then I'll put this up here. And I'll go like this. So let's suppose that I have something that's really insoluble. I'm going to just pick this. I hope that this is insoluble. Let me go look it up. Because I sure don't know. It's not listed in my table, so I don't actually know. So let me pick something that is listed here. And then I need something that I have. Okay, I could do that. Yeah, that'll work. Okay. So KSP for this is 7 times 10 to 20 minus 29. So this is essentially super insoluble, right? But if I go over here to this screen, why didn't it window capture? That's weird. Oh, I'm on a different thing. That's why. There we go. So if I look at this and I say, okay, well, I want to increase the solubility of this. Can I make a complex out of this in aqueous solution? And so I'd look for lead in my list here, and oh, here it is down at the bottom. I actually thought this was lead, it's platinum. So if I add iodine to this, so for example, I could add sodium iodide, then what would end up happening is that for this equilibrium, now I have a new equilibrium that occurs, and I don't like how I wrote that, so hold on. All right, let's get a new color here to illustrate what I'm doing. That's not different enough. That's better, okay. If I add iodide to this, then I make this complex. And KF for this is ginormous. Well, relatively speaking, it's 3 times 10 to the minus 4, or 3 times 10 to the 4. So in other words, what's going to happen is that all of this is going to get consumed and go in this direction, which forces this reaction to go in this direction. and you end up with a sort of situation where you have multiple equilibria pulling each other. This is kind of like what we did in the second lab, where we had the dynamic equilibrium with the dichloromethane and iodine solution, where when you titrated your organic layer, you're actually titrating the aqueous layer, because your titrant is ionic and it doesn't dissolve in the dichloromethane. But if you add an aqueous layer on top, some of the iodine will get pulled out, because you know the distribution constant between the aqueous and the dichloromethane layer for iodine was like 180, I don't know, it's 180 or whatever. Some of the iodine must go into the aqueous phase. If you react to that, then you disrupt the equilibrium and you pull more of that iodine out, and eventually you pull all of the iodine out of the dichloromethane layer. This is more or less the same principle. By forming this, I pull this stuff out of the solution, and I need to replace it so more PBS will dissolve. So we can control solubility not just by playing with acidity, because we said earlier, if I reacted this with an acid, like these are both things that I could react S2- with. So I would reduce this in solution as well, which would also cause this to dissolve. So this is one viable option, but this is another. Maybe you have other things in there that you don't want to like add acid to because they'll react, but they're inert to, say, iodine. So this is just an option. It's nice to provide options, right? All right. All right, that's where all I have for today. So when we come back on Wednesday, we're going to actually start chapter 16, but I am going to talk through the rest of these slides because there's really not all that much left to talk about. So here's our ammonia. If we add ammonia, we can precipitate, or not precipitate it out. We can dissolve this by forming this complex, because the new KF for this process is much bigger. Yeah, that's really all I care about. So we're going to briefly talk about multiple equilibria. We'll talk about photography. We'll talk about your teeth. Yeah, all sorts of stuff. This is unfortunately the application part, and I'm mostly going to skip over all the math, but it's nice to just see some things that you can do using these equilibrium problems that are just practical, because like people like photography, right? And people I like my teeth. Brush your tusks, be a good orc, right? That's what we want you to do here. I want to thank everybody for coming out to the lecture. As we start to get towards the end, make sure that you're keeping up with all the work, but also make sure that you are starting to like go over 161 topics that you may or may not be as familiar with. So you've been using most of the stuff, I would say, that's relevant. So like you can calculate molarity, you can turn grams to moles, like you got all the stoichiometry stuff under your belt. We even did some thermo when we talked about delta G and its relationship to K. We're going to do a little more thermo in electrochemistry starting on Wednesday, when we relate the potential of a battery to spontaneity. So we're going to see delta G again. But like delta H stuff, delta S stuff, like go refresh on that. Make sure you remember how to do a Lewis structure. Make sure you understand like SPDF electrons, like how we do all that stuff. And then like at that point, that's basically chemistry, right? Like those are more or less all of the relevant topics. And if you can touch on all of those and do well on the final exam, or you will do well on the final exam, you'll get a good score. And remember, it's curved. You don't have to get every question right. So, all right, I guess it's time for that music here. So we'll do that. Have a wonderful rest of your day. It looks like the sun might be trying to come out, so go enjoy the heat. Spring's only here for a little while, right?